In this section, we're going to discuss the ideas of abstraction and encapsulation, which were introduced in the introductory section. Abstraction is the idea of hiding or eliminating unnecessary details behind a face, technically known as an interface, that external or client code sees and uses. GUI, which is a graphical user interface, hides significant amount of details and allows you, the user, to just click some buttons, move a few things around, and you get significant behavior in the program. The details of what's really going on are well hidden. An automatic transmission is a physical entity that works. Most of us don't know how. Most of us couldn't figure it out if we had to, yet its function is something we depend on every time we drive. It knows what to do, when to do it. It just works. When we design a class, we also have to focus heavily on what not to include or eliminating unnecessary details. For example, if we're modeling a student in a university setting, hair color probably isn't significant, but a GPA or test scores are very relevant. We definitely have to keep track of those, but hair color, shoe size, not so important. We can eliminate those. Good software engineering includes both what to include and what not to include. That all falls under the idea of abstraction. We have an abstract entity that is minimal yet complete in what it represents. Encapsulation is the idea of bundling all needed data and operations on that data into one unit. This is called a class. There's a description of data and how to manipulate that data. An active unit, known as an object or an instance of the class, knows everything it needs to do for its particular job or tasks, knows where to find missing data. That's the idea of collaboration. That is where multiple objects of same or different classes communicate and share knowledge. A client of an object is not expected to know anything beyond the basic ideas of initialization and calling methods or manipulation of the object on its public interface. In the introduction, I talked about the human body. We can consider two humans meeting and say shaking hands as that idea of interface. That doesn't require any knowledge of the heart, the lungs, the blood flow, etc. But that's how they meet and that's how they communicate, verbally, handshakes, etc. That's similar to objects collaborating. They have a certain external behavior, but the internals are unknown to each other. How an object does its job is a problem that class designers and coders deal with. Designers and coders of other classes don't need to know, should not know, and they must never depend upon how a specific class works, only that it works. One major advantage of object-oriented programming is code reuse. Good classes can be reused, adding additional functionality by tweaking the source code slightly, or maybe even a lot, but built upon a base of already working code. When properly used, the benefits of abstraction and encapsulation become apparent. Classes have no extraneous details, no external requirement on handling the details of the class. That is, external code doesn't know anything about the internals of the object, nor should it. And a simple, consistent interface with which to interact with them. All of you have experienced the problem with inconsistent interfaces as operating systems have new releases or smartphones have new releases. All of a sudden, how do you interact with the device changes. Buttons are in a different place. Options change. It can become confusing. Good software design minimizes that change that external clients see, yet is able to continue to reuse the basic code. Reuse is a great way to handle the changes in maintenance. Maintenance usually means fixing bugs and adding new features. Reusing existing code that's already been debugged and proven is a great way to prevent introduction of new errors or excessive labor in the changes. And finally, client usage. A class should be usable in different programs. That's one of the hallmarks of good class design, is that you develop a data type that is good enough that multiple problems can use it in their solutions even though those particular programs may not be related at all. Just imagine for the moment the string data type that has been created and provided to Java programmers. Strings are very valuable. Many different programs use them. In creating objects, we have to have special ways of initialization. Those are method-like constructs called constructors. We generally have ways to access data internal to an object. That's called an accessor method. We have ways of changing that data inside an object. That's called a mutator method. We have a special type of accessor called a computation or a computing accessor that actually takes existing data in the object and synthesizes it into a new value. For example, if we were storing the length of some physical entity in an object and stored in feet, we might want to know the length of that object in meters. And we would not have to save the length in both feet and meters. We'd simply do the computation and convert feet to meters. And finally, this special type of accessor called a predicate accessor. It really just means it's a true false kind of situation. We might have a data container and we want to determine, is it empty or does it have at least something in it? So a predicate accessor would be named perhaps is empty. We'd say, is the container empty? If so, true. If not, false.